Hey everyone, welcome to The Explainer. Today, we are embarking on a really fascinating mathematical journey. We're going to dive deep into the processing of random signals. And honestly, you can think of this whole thing as an epic quest to tame chaos. If you've ever wondered how engineers and scientists actually make sense of all the erratic, unpredictable data floating around us, everything from the literal static on a radio to the super complex fluctuations of a human voice, well, you are exactly in the right place. We're going to use the raw power of mathematics to find actual order in what looks like total absolute randomness. So, think about this for a second. It all begins with a central, almost philosophical question. How do you extract a perfect, clean signal from a massive sea of random noise? I mean, by definition, random signals are inherently unpredictable. You can't just plug them into some simple static equation and magically know exactly what's going to happen next. But, as you'll see today, we have mathematical tools that give us the incredible power to find the hidden patterns lurking just beneath the surface. Sure, we can't predict every single data point perfectly, but by relying on probability and statistical expectations, we can absolutely master the rules that govern the chaos. Okay, let's dive into this. Here's our roadmap for the journey. First, taming unpredictable random signals. Second, power spectral density. Third, the optimal Wiener-Flichter. Fourth, adaptive algorithms. And finally, parametric modeling. Starting right off with Section 1, taming unpredictable random signals. This is all about measuring the footprint of chaos. Right, so here is the absolute foundation of our entire problem-solving framework. When we don't know the exact signal at any given moment, we can't rely on traditional deterministic math. It just doesn't work. Instead, we have to rely on its statistical footprint. You see, a random signal's instantaneous value is, by its very nature, completely unpredictable. What you're seeing is really just one realization of a much larger stochastic process, and that process is governed entirely by the laws of chance. But here's the secret. While the exact instantaneous value escapes us, we mathematically define this stochastic process using continuous random variables. We describe these variables using a probability density function, or PDF, which perfectly integrates to 1 over the entire space of possibilities, along with its corresponding cumulative distribution function. It's kind of like tracking an animal in a dense forest. You might not actually see the animal itself, but the mathematical tracks tell you exactly what it's doing over time. So, how do we actually build those tracks mathematically? Well, we start with first-order statistics. These give us the mean, which is mathematically defined as the expected value of x of t. We also calculate the variance, which is the expected value of x of t minus the mean all squared. That basically tells us how widely the signal disperses from its center. But, and this is crucial, to really understand a dynamic signal, we absolutely need second-order statistics. This involves comparing the random variable at 2 completely different points in time. The core concept here is autocorrelation. Mathematically, autocorrelation equals the expected value of x of t1 multiplied by x of t2. And that equation is incredibly powerful because it tells us exactly how the past of a signal influences its own future. Now, calculating all these statistics is great, but dealing with them constantly changing is exhausting. And that brings us to a beautiful mathematical state called stationarity. A signal is stationary in the strict sense if literally all of its statistical properties are completely invariant over time. They don't change. But for most of our engineering math, we actually just need wide-sense stationarity, also known as second-order stationarity. For wide-sense stationarity, we only require 2 strict mathematical conditions. The mean must be a constant, and the autocorrelation must depend only on the time difference, or lag, which we call tau, rather than on absolute time. Once the statistical rules of the signal stop shifting around and rely only on that time lag tau, we can finally build reliable systems to process the whole thing. Moving right along to Section 2, power spectral density. We're going to start seeing the unseen in the frequency domain. All right, up until now, we've been tracking our signals strictly in the time domain. But to truly master it, we need to transition over to the frequency domain to understand how the signal's power is actually distributed. We generally have 2 main ways to calculate this power spectral density, or PSD. The first method is the periodogram. Mathematically, this takes a time-windowed signal, calculates its Fourier transform, and then computes 1 over n times the magnitude of that transform squared. The catch here is that this result is random for each realization, so it requires a lot of averaging. The second method is the correlogram. Instead of doing direct Fourier transforms on the raw signal, it first estimates the autocorrelation sequence within a time window, and then takes the Fourier transform of that specific autocorrelation sequence. Now, both of these methods work because of what is honestly one of the most profound plot twists in all of signal processing math, the Wiener-Khinchin theorem. This theorem states that the power spectral density of a stationary random process is exactly equal to the Fourier transform of its statistical autocorrelation function. Think about that. Mathematically, it proves that autocorrelation in the time domain and power spectral density in the frequency domain are literally just two sides of the exact same mathematical coin. It's brilliant.
So what happens when we take our random signal and push it through a linear time invariant or LTI filter? Well, the filter fundamentally shapes the signal's statistics. The power spectral density of the output mathematically becomes the PSD of the input multiplied by the squared magnitude of the filter's transfer function. We are quite literally reshaping the chaos using that transfer function. But of course, this immediately begs the question, if we have the power to shape the output, how do we mathematically shape it perfectly?
Which perfectly sets up Section 3, the optimal Wiener filter, our quest for the perfect mathematical filter. Picture this. We have a noisy, random signal, and we have a desired, clean signal that we desperately want to extract. Our goal is to design a filter that bridges that gap perfectly. In this context, perfect means strictly minimizing the mean square error, minimizing the expected value of the error squared. And the mathematical secret to pulling this off is the principle of orthogonality. If we set the derivative of our error function to 0, we can mathematically prove that to minimize the error itself must be orthogonal to the observations. This basically means the expected value of the error multiplied by the observation exact equals 0. Now, when we actually expand out that expected value, we arrive at the famous Wiener-Hopf equation. It states that the optimal filter weights equal the inverse of the autocorrelation matrix of the input observations multiplied by the cross-correlation vector between the observations and our desired training data. It is a stunningly elegant, perfect solution. However, there's a massive catch. To solve for those perfect filter weights, you absolutely must invert that autocorrelation matrix. That means solving a system of M equations with M unknowns. And let me tell you, when you are processing millions of data points in real time, that matrix inversion is computationally massive. Sometimes it's just not feasible. So we're stuck asking ourselves a very practical question. Inverting the matrix is way too complex for lots of real-time applications. Is there an iterative, practical way to get to that same optimal filter without doing all that heavy mathematical lifting at once? Enter Section 4, Adaptive Algorithms. These are the street-smart, iterative alternatives to our matrix problem. Instead of trying to calculate the entire perfect matrix inversion in one giant leap, adaptive algorithms use a really clever concept called stochastic gradient descent. Imagine you are totally blindfolded on a mountain, and you want to find the lowest point in the valley. Instead of needing a satellite map of the whole mountain, which is essentially what the Wiener filter does, you just feel the slope with your feet and take a step downwards. This is exactly how the least mean squares, or LMS, algorithm works. We initialize our filter, calculate our instantaneous error, and update our weights using a specific adaptation step size called mu. That mu dictates exactly how big of a step we take down the mountain on each and every iteration. Now, the LMS algorithm is awesome, but if your starting point on the mountain is super far away from the bottom, taking small steps based only on the instantaneous gradient can mean incredibly slow convergence. That's where the recursive least squares, or RLS algorithm, comes to the rescue. RLS is mathematically much more sophisticated. Rather than just moving down the instantaneous gradient, it recursively updates the inverse of the deterministic correlation matrix itself. Because it's constantly refining this inverse matrix on the fly, it adapts incredibly quickly and completely overcomes that slow initial convergence we see with LMS. Finally, we reach Section 5, Parametric Modeling. This is where we learn to find the literal DNA of the signal. Okay, so far we've talked a lot about analyzing and filtering random signals. But what if we want to play creator? What if we actually want to synthesize our own specific random signals from scratch? To do this, we start with a base material, Gaussian white noise. Think of this as our raw clay. Mathematically, Gaussian white noise has an autocorrelation function that's just a Dirac delta function, a single, sharp spike right at 0 lag. And because of that, its power spectral density is completely flat and constant across all frequencies. We then take this raw clay and pass it through a forming filter. This filter acts as our mathematical sculptor, shaping that flat, featureless noise into the exact synthesized random signal we desire. And this brilliantly illustrates the three main parametric difference equations we rely on to build these models. First up is the autoregressive, or AR, model. The math here predicts the current output strictly as a weighted sum of past outputs, plus the current noise. Second, we have the moving average, or MA model. This one generates the output as a sum of current and past noise inputs directly. And finally, the ARMA model is the ultimate combination, utilizing a recursive equation to leverage both past outputs and past noise inputs simultaneously. It's a full ecosystem. So, how do we actually build the AR model in practice? We rely on the Ewell-Walker equations. When we arrange the autocorrelation values of our desired signal, they form a highly structured matrix known as a Toeplitz matrix. The really brilliant property of a Toeplitz matrix is that it's completely symmetric, and all the elements along its diagonals are absolutely identical. This incredibly unique diagonal structure makes solving the matrix for our filter parameters incredibly computationally efficient. But, of course, nothing is ever perfectly simple, right? While the Ewell-Walker equations make the AR model neat and linear, finding the parameters for the moving average, or MA model, is mathematically way harder, because taking the expected value for MA models involves products of unknown filter coefficients. The whole problem becomes strictly nonlinear. You can't just solve a simple matrix. It requires complex, nonlinear optimization algorithms. But if you can solve that nonlinearity within the combined ARMA model, you unlock an incredibly powerful tool for synthesizing almost any random signal imaginable. And that brings us to the end of our journey today, leaving us with one final provocative thought. We started out looking at total chaos, but we've seen that through stationarity, the absolute mathematical elegance of the Wiener-Kinshine theorem, optimal filtering, and parametric equations, we can map, minimize, and even perfectly synthesize these signals. So, if we can literally sculpt raw white noise into perfectly modeled patterns using math, are random signals ever truly unpredictable, or are they really just waiting for the right equation? Thank you so much for bringing your focus and joining me on this explainer. Keep questioning the chaos around you.